of ATS 503 data assimilation. This is a very important subject. All that you have studied so far now during your MSc, now whether it was dynamic meteorology, whether it was physical meteorology, whether it was modeling of atmospheric processes, all that is applied here. The name of the subject itself says that numerical weather prediction, right? So that means how to predict the weather numerically. That's what the theme of the subject is, how to predict the weather numerically. Because the weather was predicted earlier using so-called synoptic charts. Have you heard about the synoptic charts? In old days, when
Yes, sir.
computers
Yes, sir.
computers were not available, then people used to manually plot the weather information on the big charts, and then after plotting the observation, they used to analyze it by hand manually. And in the operational offices like IMD, you could see that there are different sections and different categories of employees. Like the junior most employees were assigned the task to plot the weather observations which used to come continuously from all over the world through old style teleprinter. Through teleprinter it used to come the old observations, and then they were plotted by the so-called data plotters or the so-called Met assistants now, who used to be the junior most staff in the IMD. So they used to plot manually the observations at all locations. Each observations had some standard code like station code, time of observation, etc. So after they have plotted the entire observation on the big maps, then a senior level people, so-called the Met analysts, they used to analyze the observations manually using pencils, draw lines, like they used to draw isobars, okay, they used to draw isotherms, and then they used to also connect the streamlines, the wind flow patterns, etc. So you might not have seen those charts when you visited IMD. Uh, uh, those charts, you might not have seen, because earlier that was the way. I mean, that was about 20, 30 years ago. I'm talking about 20, 30 years ago. Most of these centers globally, that was the way they used to do. So after they used to draw the lines, isobars and isotach and then isotherms and streamlines, then even further higher level meteorologists and all, the so-called Met grade 2, they used to say meteorologist grade 2, slightly senior level officers and all, then they used to see the charts, and then from looking at the charts, they used to manually conclude or try to just connect physically that what is happening in the atmosphere, how the weather patterns are now moving, and then accordingly they used to just issue forecast based upon their knowledge, experience, and then what they see on the chart. There was the manual way of forecasting earlier, about 20 to 30 years ago. But after computerization of all these things, now everything is done automatically by computer. All that I said, that plotting of the observation, etc., they are also done nowadays, but then that is done by computer. When the analysis, like you have learned the grads, right? The grads which you can use to draw the isobars and streamlines and wind vectors, etc., right? So everything is done now also same way, but then it is done by the computer automatically, and it is done in a much more neater way. So that transformation from the manual forecast to the numerical forecast, which is supposed to be more appropriate, because when we say the numerical forecast, then we use the numerical model, right? And numerical model is made of the sound physical principles, the dynamical principles of the atmosphere, right? And so many kinds of parameterizations, etc. So, and then also it is not supposed to change, in the sense that suppose when you do the manual forecast, what one of you will issue or conclude or draw an inference from the weather chart may not be the same as another person does. Like what Haritasri draws the inference from the manual chart, the same inference Gitesh may not be able to draw. He may have slightly different inferences, right? Slightly different forecast. Although the major things will be the same, but there can be minor variations because manual changes, manual variation. But when you use the model, then the output of the model is the same, right? And so there is no variation. Although there can be some variation in the interpretation because it is not always left to the model to do everything, but there is always some kind of man-machine mix-up. Now, when we finally issue the forecast, there is some kind of man-machine mix-up. So, but then still, what you issue eventually, or what you decide eventually, that what is going to happen tomorrow or day after tomorrow, or say 3 days from now, or 7 days from now, or 10 days from now, it is more like an objective forecasting rather than the subjective forecasting which we used to try earlier. So that is the numerical weather prediction, right? And the data assimilation is another tail attached to this subject, numerical weather prediction and data assimilation. Now, data assimilation is a very important component because the entire NWP system, in fact, you can say divide into two parts. Now, one part is data assimilation, another part is the weather prediction, which is based upon the model. But in the data assimilation, all the data which you get every day, millions and millions of data which we receive from throughout the world, that is quality controlled and then processed and then assimilated in the model, so that you have got a very good initial condition. You might have heard that the numerical weather prediction, NWP, is a initial value problem, right? Initial value problem. So unless you have a very accurate initial condition, your output will not be accurate. And for that, data assimilation is very, very important, right? So it's a very big topic, and it requires a team. In fact, most of the NWP centers, whether it is IMD or NCMRWF or even abroad ECMWF or NSEP or JMR, talk anywhere. If you look at the structure of those centers, you will find that at least 50% of their staff, scientists, work on the data assimilation, because this is a very, very important part. And it requires a lot of knowledge of statistics, mathematics, because assimilating the data is fully based upon the mathematical statistical formula. So we'll study about that. So numerical weather prediction and data assimilation. So in other words, you can say that whatever you have studied so far in the dynamics of the atmosphere and the physics of the atmosphere, it eventually culminates into the application in numerical weather prediction, which is directly utilized by the people, by the public. Okay. So this is about the basic of the NWP. I will talk about the history of NWP later on. Probably we have talked about that earlier in the class, but we shall once again talk if required. But how the first attempt on NWP was made way back in 1922 by L.F. Richardson. Did I talk about that earlier? Do you remember that? Are you all listening to me?
Yes, sir. Yes, sir.
Sure.
Yeah. So L.F. Richardson is supposed to be the father of NWP. Right, exactly. And I've told you the story, right, in the class in the previous semester. Yes, exactly. So L.F. Richardson made, I got some message, sir, my laptop's microphone has issue. Who is that? Nazmin. Okay. But Nazmin, I hope you are able to hear me. Is your laptop issue solved? I mean, microphone issue is solved or not? You say I can't talk. So, okay, but if you can hear me, that's fine. Okay, so good. So what I was saying is that L.F. Richardson is considered the father of NWP because he made the first attempt in 1922 using a team of scientists in those days to calculate each term of the dynamic equations and then connecting each terms and finally trying to obtain the solution of the differential equations, whether it is a momentum equation or whether it is a thermodynamic equation for the temperature forecasting or for the moisture continuity equation for the humidity forecasting or the wind forecasting from the momentum equation. all those things, he tried to calculate manually. And his first attempt was to make a prediction of the surface pressure. Now, so I told you the story last semester. You might have, you might recall that he tried to compute the surface pressure. What would be the surface pressure after say 6 hours? That's what he tried to do using a very big staff, about 50 to 100 people in his laboratory, assigning each of them different tasks of computation and then trying to pass on the information to another one and like that. So after all that attempt, he took several days to make a forecast of the surface pressure after 6 hours. But even after that, the forecast that he got of the surface pressure was way back, wrong, totally wrong, because there are so many issues in the solution of the equation that he used. And we have discussed earlier about in the modeling of the atmospheric processes class that the equations are also containing the solutions of the fast moving waves, like the gravity waves, like the sound waves, which are not important for the atmospheric motions. What is important for the atmospheric motion? You remember that? You have talked about that. Can you remember? Yes or no? Who
Yes,
can
sir.
tell? Yes,
Yes, sir.
who can tell that what is the most important wave that is affecting the atmosphere, whether it is a sound wave, whether it is a gravity wave, whether it is a Rossby wave, whether it is a Kelvin wave, which wave is most important? Do you remember that? In the last semester we had talked about that. Kelvin, can anybody tell?
I think it's a gravity wave.
No.
No.
Next. Now only few choices are left.
Rossby.
Rossby, yes. Actually, it is the Rossby wave is very, very important, especially for the large scale atmospheric motion. The Rossby waves are very important. Whatever you see, say for example, the western disturbances, movement of the western disturbances, actually they are the manifestations of the Rossby wave, right? Even the big monsoon circulation is also affected by the Rossby waves. Like you might have seen that, suddenly the monsoon becomes very active, right? And there is torrential rain in some part of the country, especially when the monsoon trough is hovering over the northern part of India and there is a western disturbance is passing. Then the monsoon flow is generally easterly, and the western disturbance is a westerly current. So the two interact, and then they give rise to big, tall, deep clouds, and there is torrential rain. Also, many times it triggers the cloud burst over the mountains. So Rossby waves are very important, which goes on down the year. There are big waves circling the whole Earth all the time. And if you just see the global chart, you can count the waves actually on the global chart, about 4 to 5 waves circling the whole globe. So whenever that wave comes over Indian region, then we call it the western disturbance. So the Rossby waves are the most important for the atmospheric motions. Of course, the gravity waves, as Hartasri said, they are okay, important, but that is important for a small scale, like when there is a thunderstorm, then gravity waves can be triggered by thunderstorms, right? So that it becomes important at a higher resolution. Okay, gravity waves can also be triggered when there is a flow over the mountain. Now you have read about the mountain waves, right? The Lee waves.
Yes, sir.
Lee waves, etc. They have heard about that. So gravity waves get triggered, over the mountains. The gravity waves get triggered by strong convection, thunderstorms. Sometimes also during the cyclone, gravity waves can get triggered. So gravity waves becomes important at at a higher resolution when the scale of the phenomena is smaller, right? And it is much more difficult to model than compared to the large scale Rossby waves, right? So again, there is a separate issue on that, how to handle the gravity waves. But normally, now when we are doing the NWP, especially for the large scale NWP, global scale NWP, now we try to use the filtered equation, right? You have heard about the filtered equation, right? You've studied about that earlier, filtered equation?
Yes, sir.
Yes, exactly. Yeah, last semester you studied about the filtered equation, and filtering means we try to filter out the unwanted waves, right? The unwanted gravity waves, unwanted sound waves. So Richardson's solution contained all these unwanted waves, and as a result, his solution of the equation was masked by all these unwanted things, unwanted noise, and his results were at least 4 to 5 times higher than compared to the actual surface pressure change, right? So you can read the history of NWP from the reference book which I have given you in this PDF. I will mail it to all of you, or maybe Arthasri can mail it to all of them. The file which I have mailed to Arthasri, she can circulate to all others also as
Sure.
as a syllabus. So in this syllabus, if you can see, I have again, can you just scroll down, Hartasri, because now the control is in your hand. Scroll down the syllabus. Yeah, about 23 lectures, although are there, but as I do in the earlier semester, these lectures, one lecture can be divided into several sub lectures, like lecture 1, for example, can be 2 or 3 lectures. Or this lecture 11, I see the physical parameterization schemes. This one lecture actually will take about at least 7, 8 lectures or 10 lectures. So like that. So even though here in the schedule it shows about 22, 23 lectures, but in actually it will become quite large, maybe 40, 45 lectures will become total. So this is how I have planned. So go down further, Arthasri. Scroll down. Yeah, and you can see the textbooks. No, so you see the Holton is there on the top, right? Holton is the Bible, like So it is there everywhere, whether it is dynamic meteorology, whether it is modeling of atmospheric process or whatever. It is always there. NWP. So Holton is one of the important reference book. Then Numerical Prediction and Dynamic Meteorology is by Haltiner and Williams. It's another very basic book on NWP. Okay, so then third is numerical methods used in the atmospheric models. This is a good WMO GARP. This is a very important book. If you can get that from the internet, from the WMO's archive, that is a very, very good book. Numerical methods used in atmospheric models. Then numerical weather prediction by P.D. Thompson is also a very good book. Then Eugenia Kalne. She is the author of this data assimilation. She worked at NSEP earlier. Now she is at the University of Maryland. So these are the reference books. And then at the bottom, you can read that it is a NWP lab practical. Okay. So we shall try to do these practicals, which includes numerical differentiation, integration. Now the internship, you have been given this Fortran syllabus for the NPTEL course, and in that, as you say, that after 1 week, he's talking about the integration. So we shall try to learn the integration. That is very useful by simple examples, as an application in the atmospheric models. Numerical differentiation. Also, you have already studied, last semester. How do we do numerical differentiation by using different techniques like finite difference, finite element, spectral, right? You have studied those things. We will try to compute the divergence and the vorticity, small examples, just to make you learn that how to compute the divergence, because everything is there in the model. When you run the WRF model, all the diagnostics are there inbuilt in WRF model, because once you run it and post-process it, you will get the outputs. But you must learn how that is done, right? Otherwise, running the WRF model will become like a black box, right? Therefore, it is important that you learn how those things are computed basically. So you try to do those exercises in your class, practical class. Stream function, how do you calculate? You have studied the stream function and velocity potential, right? In your dynamic meteorology class, you have studied about, you just recall. So you have to keep your all your earlier lectures fresh. You have to go back and refer to those lectures of dynamic meteorology, lectures of physical meteorology also, and modeling of the atmospheric processes, to be able to learn this subject, more clearly and do the practicals. Then we shall try to implement, some simple weather prediction model and climate models like WRF, which can be used for both the modes, in weather prediction mode as well as in climate mode. Although people use some other climate models now, like RCM and many others, but even WRF can be used in the climate mode to run the climate model. Then data acquisition, simulation of idealized cases, that is very important. I think all of you should be able to do this exercise, because if you do that, simulation of idealized cases, like how does a wind flow over a topography looks like? What is a baroclinic wave? How does it look like numerically in the model? What is gravity waves? How does it look like in the model? A square line, how does it look like? How can you simulate the sea breeze? How can you simulate the sea breeze numerically, right? Large dissimulation, etc. So all these are idealized cases. Before you run the real case by WRF model, it's good to uh, learn the idealized cases, because this will give you a lot of insight of the problem, and then also make you learn the basics, fundamentals of the NWP. So these are the practicals which I'll try to learn as much as you can during the semester. So Hartasri, just scroll back and go to the top. Okay, so now in the lecture 1, it says Introduction to NWP, Data Acquisition and Quality Control. We shall talk more about that in our next class, because today's class is almost going to end. Then numerical methods, finite difference techniques. Now this you have already studied in your last semester, right?
Yes,
Yes
sir.
or no? Yes, exactly. You already studied in your last semester
Yes.
the numerical methods,
Yes.
that is finite difference, finite element, spectral, etc. So we will not repeat these things, but you keep in your mind that you will read those old notes or PowerPoints or books, whatever related with this, because even though I may not repeat the lectures here in this semester, but you can expect questions in the examination. You can expect questions on these topics because it has been taught already. You understand that? So you have
Yes,
to,
sir.
yeah, you have
Yes,
to
sir.
refresh, yeah, you have to refresh yourself. Then numerical prediction models, also something you have already learned in the last semester. We have, I think, talked about different types of numerical models, right? I think we discussed about the equivalent biotropic model. Did we discuss about the equivalent biotropic model in the last semester?
Yes, sir, we did. Yes.
Yes,
Exactly.
sir. Yes, sir. We
Yes,
have.
Okay,
sir.
yeah, right. So this equivalent biotropic model, quasi-geostropic model, primitive equation model, right? Those things you have already studied, right? Two-level model also, right? So no, you have to refer back all those things, from your previous semester's lectures, and then you can discuss. If you have any doubt, once again in this semester, because these are the important foundations of NWP. Then governing equations in Cartesian coordinate, also you already know that, because you have studied the various vertical coordinate systems, right? The P coordinate system, the Z coordinate system, the sigma coordinate systems, and so on. So how the governing equations look like, in those systems. So Cartesian coordinate is basically the Z coordinate system. So you already learned about that. So these things now is, we will not repeat those things, but we can just have discussions like now in the Google class. We can have discussions. We can have assignments, sort assignments, so that it will keep you, in touch, and keep you fresh. Right, tool dimensional barotropic model also, we can discuss if you have not discussed earlier. Baroclinic model, that is the two-level model. Then discrete formulation of horizontal and vertical mixing in the atmosphere, basically discretization only. Discretization also you have studied, because there are a lot of overlapping. NWP actually, as I said, consists of modeling of atmospheric processes as well as other things like fundamentals, dynamics, and physics. Then short, medium, and long-range deterministic weather forecasting. Well, we shall talk about that, although more or less you know about this, and in some way or the other, we have talked about that earlier. Then physical parameterization schemes. We shall try to talk, in an elaborate way. I think some of you, did you attend the lectures last semester when I was taking lectures for your senior batch? Did you attend those lectures? Of physical parameterization schemes. I remember some of you were sitting in the class. Do you remember that?
So
Like,
we attended the PBL lectures.
Yes, sir.
okay. Only PBR or any other also?
No, sir, only
No,
PBL.
sir, only PPL.
Oh, I see. So no problem. Then,
That too, sir, on the
okay. So we can once again repeat the lecture because this is very important, and there may be about 8 to 10 lectures now to cover all the physical parameterization in a very short manner, not in detail, of course, because detail if we go, then each physical process will take one semester. So we shall do that. Then predictability is a very important topic. We shall talk about that in detail. The limited area model, well, we shall talk about that. Your WRF is nothing but the limited area model, right? Before the models like WRF or MM5 were available, people used to have a LAM. LAM is limited area model. So we shall once again talk about that briefly. Then probability and ensemble forecasting is another very important topic. Probability and ensemble forecasting, because nowadays this is the key to the successful NWP. Because one model is not good enough or perfect enough to give you the accurate forecast. So we have to use ensemble model. So we shall discuss about this in detail. Then starts the data assimilation, very important topic, right? Very complex and very important topic. So we shall talk about that, the basics of the data assimilation, variational assimilation, ensemble-based assimilation, Kalman filtering, sensitivity analysis. Well, those things we can discuss. They're cool topics. Estimation theory, 3D var, 4D var. Again, shallow water and its adjoint, that is related to, again, assimilation, radar data assimilation, basics. So I'll just talk about the basics because again this is a vast subject. Ocean data assimilation also we shall talk the basics of ocean data assimilation is again another subject mostly done by the ocean modelers, especially at INQUAS, very strong group which works on ocean data assimilation. The assimilation of the altimetry data, we shall talk about that a little bit. So with that, your NWP and data assimilation course will complete. Okay, this is the lecture plan. All right. So for today, I think we better stop, and then from the next class onwards, we can talk more in detail starting from the first lecture. So you have any question, any of you? Discuss in another 4 or 5 minutes, and we can talk about if you have any doubt or any questions. Is everybody okay, comfortable?
Yes, sir.
See that all 11 out of 13 people are there. So only 2 are missing. One is Vibhuti and who is the second one?
Anish.
Sir, Anish.
Anish got worked out. See, before calling. So anyway, I'm trying to record and then I'll put the recorded version on the cloud like last semester I do. I'll give you a mail of that link of the lecture. So those who could not attend now completely, but those who have attended also, you can once again go through that link, recorded version, to refresh your lecture. Okay, so now I stop recording first of all.